The ball is in the air for 4 seconds, so t equals 4 seconds. The initial velocity is 3t squared miles per hour.
And to find the position, we can find the integral, which is t cubed. But in this instance, we don't need t cubed because we just don't need it. And since we're trying to find the acceleration of the rainbow shot, we find a derivative of this. So that would be a equals, bring that down, it's 6t, right? And that's the acceleration formula. The graph of velocity, because v equals 3t squared, it will look like a parabola, right? And since the time is equal to 4, that means the maximum it will get is 48, right? So the t right here, t is going to be our x value, right? 1, 2, 3, 4, right? And then we draw it up to 48, which is going to be the most speed, most velocity it will get at. So it starts at 0, comes up here, comes down. When it's at the 2 seconds, that's the peak. That's when the ball will reach the highest point, all right? And it'll fall down again, all right?
All right, so we're going to find the acceleration graph using the velocity one that we already drew. It starts increasing positively, but decreasing. So we're starting up top here and going until 0, which is the point of inflection, where the slope is 0. And then it goes to decreasing velocity, or acceleration, which is in the negative point of the x-axis.
We're going to make a position graph, right? But this has nothing to do with our original problem, which is finding the acceleration. But just because we're going to make the position graph, right? So because we know this one is 3t squared, right? This one is 6t, right? This one has to be t to the cube, then, right? T cubed graph, same thing as x cubed, right? It'd be going up, down, and up again, right? In order for our graphs to be accurate, we have to draw them like this. But because time cannot be negative, for the sake of this video, we're just going to make it so that this right here and this right here doesn't exist. So then for a better representation, our parabola is going to be coming out like that. But in actuality, we deleted this part. Okay, same thing with the graph right here. It's supposed to be like that. All right. So for our purposes, since time can't be negative, we're going to cut it in half. All right. All right. So at this point, we're trying to find the POI of this rainbow hit, right? So I'd write here when it crosses into the positive realm, right there. That is the POI. At the same time, this is concave down. Well, this thing is going concave up, right? All right, moving on. This one is going to be concave down completely, right? It's all going down. So because that is concave down, this has no POI, right? Keep that in mind because this never is not, it's always going down. It's not going up again, right? So this is always concave down. This is concave down, so the graphic acceleration is going to look like this, right? All right, so now we're going to find the concavity of the PV is, right? So for position graph, this is going to be concave down because it's going down, right? It's going down instead of up, so it's down. And right when it crosses this path right here, that's the POI, right? It's going to be concave up, right? That's POI, right? Concave up at that point, right? Going to the velocity graph, right? There's nothing here, right? There's no POIs or anything because it's going down, straight going down. So this whole thing is concave down, right?